We're going to start chapter 5 here with like a preliminary section here to kind of get us, to review some important algebra concepts that we would have talked about last year that are going to come into play in this chapter. So we're going to be talking in this chapter a lot about identities. So an identity is just like an equality statement that is valid for all values of a given variable. So one of the key things that we're going to be doing when we're kind of playing around with these identities is we're going to be relying on some of these algebra techniques from last year to develop some of these things. So we're going to review some FOIL techniques and some factoring techniques and a little bit of that kind of stuff that we would have talked about last year in our algebra course to just kind of get us primed and ready to go on this, so we refresh some of these topics that we haven't talked about in a while but are still things that the expectation is you'd still have good knowledge of but might need a little refresher on. Okay? So that's mostly what we'll do today, is just kind of run through some examples and ask you guys to try some stuff and go over some things. It'll try to be rather interactive on this because these are things that mostly my expectation is that we still kind of remember how to do. All right. So the first couple of examples are going to be foiling examples. So remember, FOIL is just an acronym for how we multiply two binomials together. FOIL stands for first, outer, inside, last. So like we multiply the first things together, y times y is y squared. Multiply the outside things together, y times 7 is 7y. Multiply the inside things together, 2 times y is 2y. We multiply the last things together, which is 2 times 7, which is 14. And then we can combine our like terms. 7y and 2y, we add coefficients, but the degree on the variable stays the same. So we end up with y squared plus 9y plus 14. Anybody remember doing this? This should feel pretty familiar and pretty good. You've probably done this in 4 or 5 different courses at this point, probably starting in middle school, that we've been foiling for a while now. Why don't you guys take a moment? We'll take a minute or so, and you guys can try to do number 2 here. As an example, just in your notes or on a scrap sheet of paper, or just in your head or whatever. If all I do is kind of pay attention and participate. You can do it on a scrap paper if you need to write stuff down, or if you just want to kind of hold it in your head, you can try to do it in your head. And we'll go through it in just a moment, okay? Just a minute or two. This should be a pretty quickie, these foiling ones. All right, let's get going on this then. So when we multiply our firsts together, we have to be a little bit careful. So 3b times 2b, we multiply the coefficients together and get 6, and we multiply the variables together and get b squared. And then the outer, we have 3b times negative 1 gives us negative 3b. The inner, 4 times 2b gives us 8b. And the last, 4 times negative 1 gives us negative 4. And then combining together, we get 6b squared plus 5b minus 4. We feel pretty good doing this stuffs. Now there are some foiling shortcuts here that we should talk about, that while you can still foil, these things are time savers and they can come up rather frequently. So it's the perfect square factoring, which says that a plus b quantity squared is equal to a squared plus 2ab plus b squared. A perfect square difference, a minus b squared, is going to be a squared minus 2ab plus b squared. And then the last one, the most frequent one we see, is the difference of two squares. So a plus b times a minus b just becomes a squared minus b squared. So these three special multiplication patterns we can use as a multiplication shortcut, or we can use it as a factoring shortcut that we'll look at here in a few minutes. Probably we're more familiar with like the difference of two squares as a factoring shortcut rather than a multiplication shortcut, but you can use it either way, right? It's equality, so that runs forwards and backwards. You know what I'm saying? Okay, so let's look at a quick little example here. So if I look at 3, this looks like the green situation to me, right? So my a is x, and my b is 3. So when I plug this into my pattern, I have x squared minus 2 times x times 3 plus 3 squared. Right, when I'm just plugging my a's and b's into that pattern down there. So that gives me x squared minus 6x plus 9. Maybe it's a little bit quicker than foiling because we didn't have to combine the like terms on that last step there. So we shaved off that part of the foiling process by remembering this pattern and using that pattern. But could I have still just foiled this? Yeah, of course you could. You'd have to remember, though, to foil it and not just try to distribute the exponents, which is very bad and makes math teachers cry. If we look at 4, what type of pattern is going on with 4? Yeah, it's a difference of two squares, right? So in this case, the a is y and the b is 5. So this just becomes a squared minus b squared, or y squared minus 25. Again, could you have foiled that out? Yeah, sure. But I'm into that whole brevity thing. So like, if I got some shortcuts that are pretty reliable and come up rather frequently, I'm going to take advantage of those shortcuts because, you know, like, I'm all about working smarter, not harder. You know what I mean? It's a great lesson in life. Inherently, all mathematicians are lazy. We want to look for the easiest way to do things. Now we'll spend unbelievable amounts of effort to find that easy way to do something, but so I guess it's, you know, like, where are you willing to spend your effort at, right? All right, why don't you guys try to do 5 and 6 here? We'll take a couple minutes and let you guys try these on your own. Try to use the shortcut to do them. Again, like, we've acknowledged that we can FOIL these things out, and that's fine. Certainly, if you forget what the shortcuts are, you could use FOIL still. Not wrong to do that. But here, the point of the matter is to try to practice using the shortcut. So take a minute, try to multiply these out using our shortcuts, and then we'll go through it together in a moment. Again, you can do these in your notes or on a scrap sheet of paper. Just kind of think about it in your head. You know, it's okay. They're your notes. Whatever you've been comfortable with is cool with Mr. Kulik. He's not going to micromanage how you're working. You know, some people are micromanagers. I'm not. I'm going to get out of the way and let you do it the way you want to do it. you know? Because I don't know what's going to be best for you. Heck, I don't even know the best way sometimes. And just like I know the way I would do it. Maybe that's the best way, maybe it's not. I don't know. I try to be open-minded. You know what I mean? It's a good lesson in life. Now, if you see somebody making mistakes, like, be like, hey, like, don't you think this would be a better way to do it? You can certainly stop and let them know. Unless they're your enemy, in which case you just let them keep making mistakes and take advantage of it. I'm talking about like if you're playing a game or something, not like a real enemy, but that's a Billy Beanism. He was the general manager for the Oakland A's. He's the Moneyball person. But that's if you see your opponents making mistakes, you don't let them know. You just let them keep making those mistakes. All right, let's, even if you're not all the way done, let's kind of start blowing through these. So the first one is the green situation. So here my A is like 2A and my B is 1. So we're going to have 2A squared minus 2 times A times B plus B squared. Now the place that we have to be careful about is the 2A squared. 2A squared means 2A times 2A. So that should be 4A squared. Make sure we're being careful on that. And then 2 times 2A times 1 is just going to be 4A. And 1 squared is just 1. 6 was the yellow situation, where our A is 3Z and our B is 4. So 3Z squared plus 2 times 3Z times 4 plus 4 squared. So 3Z times 3Z is 9Z squared. 2 times 3 times 4 is 24. And then I have a Z at the end. And 4 times 4 is 16. Yeah, Victoria.
Remember 5, why is 1 not negative?
Well, okay, so if you think about it, you're talking about this part at the end. Why isn't it minus B squared?
No, in the so that B is 1.
Okay, it's because we've already accounted for the negative sign here.
Oh, okay.
And here, right? If I plug negative 1 in for B, I'd have A plus B or A plus 1 because I have the subtraction symbol built into the formula already. The other way you could think about it, Victoria, is you could do everything as the yellow, and you can just take like this thing as like, think about it this way and use the yellow formula and use B as a negative 1. And then you could do it that way also. Does that answer your question? Okay. So again, not wrong to do it that way, but we built a separate formula because sometimes we like overkill. Lily? Of course. Okay. On to the next page then. So here we're going to talk about factoring. So you guys remember way back into our Algebra 3-4 class, we built out like that factoring diagram that told us kind of how to do our factoring. Do you guys vaguely remember that? Do you want to redraw that here? Sure. Okay. All right, just let me move over enough. So you have some polynomial. The first thing is we check to factor a least common multiple. Oh no, greatest common factor, jeepers creepers. So the first thing we do is do that. Then we look at the number of terms. And in our case, we saw 3 situations. Things where we can have 2 terms, where we have 3 terms, and we can have 4 terms. I'm going to go down the 2-term branch first. So the first thing we check for, is it a difference of 2 squares? I abbreviated that phrase as DOTS, difference of 2 squares. If it's yes, then we check each factor starting at 2 terms. Since after you finish a difference of 2 squares, you're going to have binomial pieces left. We have to check those pieces then down the 2-term branch to see if there's more factoring that we can do. So if it's not a difference of 2 squares, then we're going to check for a sum of 2 cubes or a difference of 2 cubes. If it's yes, then we check the binomial factor, the factor with just 2 terms in it, down the 2-term branch. If it's no, then we stop. There's no more factoring that we're going to be able to do. I'm going to pause here for a second, then we'll go down the 3-term branch and describe what we do there. And lastly, we'll deal with the 4-term branch. Okay. Tyler? Of course. All right. 3 terms. The first thing we're going to check for is that is it in the quadratic form? If the answer is no, we're done. There's nothing more we can do with that. At least without doing like the synthetic division stuff, right? And we're not interested in that right now. If the answer is yes, then we check the leading coefficient. To see if the leading coefficient is 1. LC is just my abbreviation for leading coefficient. If the answer is yes, then we do the short factor. If we can do that shortcut factoring, then we check the each of the factors down the two-term branch. If we can't do that, then we stop. There's nothing more to do. If the leading coefficient wasn't 1, then we have to do the long factor. If we can't do that, if the long factoring doesn't work, we stop, we're done, there's nothing more we can do. If we can do that long factoring, then we have to check each factor down the two-term branch. And again, I'm going to pause here for a minute, those of you that are writing to catch up. Not that all this stuff isn't also on OneNote that you can get at any time, but, you know, just trying to be respectful. Okay, and then the last piece was the 4 terms. Thing we check for there is if we can use factor by grouping. If we can't, we stop as there's nothing more to do. If we can use factor by grouping and it works, then we need to check each factor down the two-term branch. Again, you're going to get binomials out of that. So that's kind of our flow chart for factoring by using our by hand factoring methods, not involving synthetic division. On any of these where there's stop, conceivably you could do synthetic division in one of those situations to maybe or maybe not go further, but we don't care about that right now. That's beyond the scope of what we're trying to do. Okay, so let's go back here. So let's look at number 7. First thing I'm going to do is their greatest common factor. If I look at each 3 of the terms, is there something in common to all 3 terms? No, right? 1 you could say, but like 1 doesn't count as a greatest common factor. Okay, so then we look at the number of terms. We have 3 terms here, right? 1, 2, 3. Everybody see that? Okay. Is this in the quadratic form? Definitely is, right? You have, this exponent is twice as big as this exponent, and then there's no variable on this one at all. That is textbook this is quadratic, let alone quadratic form. So that's good. So the leading coefficient is 1. So if we can factor this, we should be able to factor it the short way. So what we're going to do is we're going to look for 2 numbers that multiply to give us the C term and add to give us the B term. And here, since they're both the same number, we'll color code. So what two numbers multiply to give us 4 and add to give us 4? 2 and 2, right? So that allow us go straight to the factored solution, x plus 2 times x plus 2. Done. Nice.
Wait, what does that say over there? It's like next to like the 4.
Oh, that's just a bracket with 2 and comma 2 next to it. Those are the two numbers that satisfy that. Let's look at 8. First thing we look for is greatest common factor. Is there a greatest common factor here?
Yes.
Yes, what is it? 2. When I pull that 2 out, what do I have? C squared plus 3z minus 54. Everybody good there? Now we're going to ignore the greatest common factor on the outside. That factoring part is done. It just comes along for the ride from here on out. How many terms do I have? 3. Is it in the quadratic form? Yes. Is the leading coefficient 1? So we should be able to do the short factor. I'm looking for two numbers that multiply to give me negative 54. Add to give me 3. Anybody see those two numbers? Which problem do you start with first? Start with the multiplication problem. So what are some things that multiply to give us negative 54? 9 and 6 will multiply to give us positive 54. So negative 54, one of them needs to be negative. Which one? The 6. Because we need 9 plus negative 6 to give us positive 3. So we have 9 and negative 6. Everybody cool with how we did that? Again, do I expect you to write all this stuff down that I'm writing down right now? No way! These should be things we can do in our head. I'm just writing all this stuff down as a refresher, so you can kind of see what we're thinking. You know what I'm saying? If you can do these in your head, that's excellent. That's what should be happening. These ones where we can do the short factoring, I hope that we still remember how to do and we can still do quickly and efficiently in our heads. If you can't, we're going to have some practice, so we can get better at it again. All right, let's look at 9. Greatest common factor? No bueno. How many terms? 3. Leading coefficient 1? No. So we have to do the long factoring, right? So we're going to need the two numbers that multiply to give us the first times the last. And add to give us the middle. So what multiplies to give us negative 24? What are some things? 8 and negative 3. That'll work, right? Those will add to give us positive 5, and they also multiply to give us negative 23. This, however, does not go straight to our answer. So what I'm going to do with the 8 and the negative 3 is I'm going to replace the 5b with 8 plus negative 3. Right? 8 plus negative 3 is still 5. So 5b can be the same thing as 8b plus negative 3b. And then I make two groups. Note that in between the two groups, you must have an addition symbol. That's why I wrote it as plus a negative 3b instead of minus 3b. In the first group, I can take out a greatest common factor of 2b. That gives me b plus 4. In the second one, I can take out a greatest common factor of -3, which gives me b plus 4. Notice now that both of these have a b plus 4 in them. So if I factor the b plus 4 out, I'm left with 2b minus 3. This is one where maybe if you didn't remember how to do that from last year right away, that's understandable. But after seeing it once, you should be able to kind of start banging those out again, right? All right, why don't you guys try to do 10 and 11 here on your own? We'll go through those in a second, and then we'll do 12 together because although it looks kind of scary, it's not so bad. Yes, sir. Absolutely. No, that's not right. There it is. So I've written down my answers for those two. Do you guys feel okay on them? Anybody want to talk about either one of the two? Happy to do so if we need to. If not, we'll just kind of keep on rolling. Rolling we go. Let's look at 12. Notice here we have some cosines in here instead of just regular variables. Does that really change anything for us, though? No. Really, when I see the cosine squared x and the cosine x, shoot, I just think about that as like 3y squared, like 13y plus 10. Really the same problem, right? Just my variable name is kooky, but like, it's all right. It's just a variable name. Just a name. You know, what's in a name? So give it a go, right? Should be able to do this now if we think about it that way. I'll write down the answer here in a moment. You may. Oh. So there's our answer. 3 cosine x plus 10 times cosine x plus 1. Do you guys want to go through this one? Okay. So again, you're looking for the two numbers that multiply to give us 3 times 10, and then add to give us 13. Anybody see those two numbers? 10 and 3, right? Hopefully that's not too hard to see. I'm just going to use y's, if that's okay with you guys, because it's just less symbols to write down than calling them cosines. And I make my two groups. From the first group, I can take out just a y. From the second group, I can't take anything out, so I'm just going to take out a 1. Both of them have a 3y plus 10, so when I take that out, what's left is just the y plus 1. Does that feel okay there? So again, the easy part to mess up was remembering to include the 3 times 10. Got to remember to do that when you get to the long factoring ones, right? You have to have the leading coefficient times that constant term at the end. Really, you're doing that for the other one, but if the leading coefficient's 1, it doesn't really matter because 1 times the constant term is just the constant term. That's why we can get away with not doing it on the short version. We're still doing it. We just don't ever say that we're doing it. You know what I mean, guys? Okie dokie. And then these last ones, won't be able to go through all these, I think, in the 7 minutes we have left, but we'll kind of talk about what's going on here and run through a couple, okay? These ones can also be done the same way that we were doing before, but the point of these ones is to point out to you that those special multiplication patterns that we identified earlier, can also be used as factoring patterns, that it runs both ways. So, for example, on 13, I see that I have a squared thing at the beginning and the end. So potentially A could be X, B could be 5, and then to check 2AB needs to be equal to 10X. So 2 times X times 5 is equal to 10X. So this is the yellow pattern, A plus B squared. Now, typically those perfect squares, factoring patterns, sometimes you see it right away and sometimes you don't notice it. It's easy to not notice them. So I don't find them that valuable. But what is super valuable are things like 14. What do you notice about 14? It's a difference of 2 squares, right? Those are the gimmies. You should be able to knock those right away, where the A is Z and the B has got to be 6. What do you guys think? Not too bad. For next time, I want you guys to work on worksheet 1, which is just practicing these foiling and factoring problems that we've kind of talked about to this point. That all sound reasonable to you guys? Again, most of these ideas should be pretty reviewed, right?